Hello, everyone. Thank you for attending the CXL Consortium's an overview of the CXL 3.x specification webinar. We'll begin the webinar in just a moment. Hello, everyone. Thank you for attending the CXL Consortium's an overview of the CXL 3.x specification webinar. Today's webinar will be led by Mahesh Natu from Intel. If you have any questions, please feel free to enter them into the question box and we will address them during the Q&A. With that, I will go ahead and hand it off to Mahesh to begin the webinar.
Hi everyone, good morning, good evening, wherever you are. And welcome to the CXL 3.x spec webinar. My name is Mahesh Nath. I have been with CXL Consortium since the very beginning. I co-chair the Systems and Software work group in the consortium, and we have come a long way right from the early days of CXL. I'm also a senior principal engineer and director of platform architecture at Intel Corporation. So with that introduction, let's kick off today's discussion. And as I mentioned, feel free to add questions in the question box as we go on. We'll address the questions at the very end of the webinar. Okay, so here's the quick agenda that I have. Let's go over the industry trends, some of the backdrop behind CXL 3.x, the environment under which we were constructing 3.x. Key themes of the CXL 3.x feature set. By 3.x, I mean 3.0, 1, and 2. Right? There's three versions of CXL 3 that are out there, specs out there. We'll talk about feature progression as to how some of the features evolved. Many of the features that we see were introduced in 3.0, and then we built on top of that in 3.1 and 3.2. In addition, when we released 3.2, we also added some brand new features, right? Just starting fresh. So we'll go over that as well. We'll touch upon compliance update, summary, and then Q&A. Okay, so let's dive in. So some of the key themes that we're seeing, right, as the CXL consortiums started looking at beyond CXL 2.0. Obviously, I don't say that AI and ML applications and heterogeneous computing, where CPUs and GPUs and other XPUs are working together, is exploding. The way the CXL 3.x addressed that is by doubling the effective bandwidth and adding some enhancements to the caching protocol that would allow these entities to work together more efficiently. We also added support for larger fabric, so you can build a very large topology with lots of these compute elements, right, thrown together, and they can work as a single cohesive unit. The second trend we saw was a number of attempts and actually even proof of concepts and some successes in disaggregating memory from the compute. There was just a lot of push for reducing the cost of standard memory in large data centers, where sometimes memory is over-provisioned. So a number of large CSPs and other customers were looking at separating memory from compute and sort of dynamically allocating the memory that's needed for a specific workload as the workload changes its characteristics. So what we have done in 3.x to respond to that is by standardizing the interface for managing pooled memory and shared memory. This allows these vendors to build such hardware and have a generic management, right, with standard capabilities, right, that meet their use cases. We also saw that there were a number of instances where companies were deploying a lower cost memory option. Like for example, DDR5 is the latest and greatest technology, right, at this point for memory from JEDEC, but many of the vendors had DDR4 memory, right? That has been sort of utilized, and but they wanted to keep running it, right? So it was lower performance, but also lower cost for them because they already sort of right, used that during their previous generations. Uh, so this in this model, what they wanted to do was be able to have an effective software turing mechanism that allows both memory, right, the DDR5 as well as DDR4 memory to be used effectively, so that the application don't suffer, right, in terms of performance. So what we've done, and I'll get into that in the 3.2 section, is by defining a mechanism for detecting hot pages. Uh, One can write generic software that can manage the memory and move pages right efficiently between these two, or even more than two memory tiers. Uh, as the security expectations and requirements keep increasing, there's much greater demand for confidential computing as various organizations are moving their workloads to cloud. They want assurance that the cloud service provider is not able to peek into their workload or into their secrets, and want to get assurance that that is the case. So there's a number of such technologies being built. What we did in CXL starting with 3.0 is add support for what we call TSP. Uh, so that allows these workloads to be placed on CXL memory devices and allows CXL accelerators to participate in the confidential computing workloads. The other thing that also happened around the same time, right, is that there were a number of other efforts for coherent I/O that were ongoing, and some were like really reasonably far along. Uh, but I think the industry as a whole decided that having multiple efforts, right, that solve the same problem, isn't really cost effective, right? So I think the industry kind of got together and then decided that let's focus all the energy on CXL for the coherent I/O. So the other efforts that are going on, C6, OpenCAP, and GNG specifically, right? Their assets and their work was sort of merged into CXL. And we'll see some of the capabilities that we added to CXL that essentially originate from some of these standards, right? A lot of work had happened there. They had made great progress, and so CXL was able decided to efficiently use some of that, right? Those technologies effectively. So that's the summary. So let's get into the details. Again, quickly the spec release timeline. We started back in March 2019 with the 1.0 release. Just a few months later, the consortium became official incorporation. We released 1.1 with few changes and compliance chapter. November 2020, you can see it's a really rapid movement, right? Because of the industry demand. 2.0 was released, highly successful. A lot of devices and components out there that support CXL 2.0 spec today. In August 2022, we got to 3.0. Soon after that, 3.1 and followed by 3.2, about a yearly cadence, right, based on the environment that we just talked about. This one again shows the industry standard conversions that we talked about. We had OpenCAP, GNG, and C6. They had a lot of good work, and all of that sort of is now flowing into CXL, and that shaped CXL 3.x specifications to a great extent. Okay, so let's talk about specific features that got into CXL, right? So CXL 3.0, a major benefit over the 2.0 was really doubling the bandwidth, right? We switched to PCI 6.05. That means we got 64 giga transfers per second, right? Transfer rate. Again, with PCI 6.0, we also moved to PAM4 to sort of simplify the transition to the doubling the bandwidth with the same clock. Again, there's other things that PCI did in terms of the forward error correction and CRC that's CXL sort of leveraged. You can show the picture on the right side, right? If you look at the PCI 6.0 flit layout, it has CRC and a forward error correction. And the CXL has two formats. One is standard format that also carries forward the 6-byte forward error correction. and also the CRC, and adds a 2-byte flit header that identifies the what's inside the packet. But very similar to PCI 6.0 layout. We also have another layout that we call latency optimized that allows the receiver to sort of pull the data quickly and start processing it before the entire 250 bytes are available. So you essentially end up with sort of two chunks, or what we call two flit halves that transfer data. So it essentially, in some applications where latency is paramount, right, this format can be used. Okay. Obviously, backwards compatibility is essential to CXL success. So we continue to support the lower data weights, 8, 16, and 10 giga transfers. And again, the previous devices that are built to 2.0 and 1.1 continue to work with the 3.0 hosts. So let's get into the 3.x feature application. Again, we're going to talk about features that essentially had a beginning in 3.0 spec release. We enhanced a little bit in 1.3.1 and 3.2, right? So we'll see the progression for many of these features. So the first amongst that is essentially the scale, right, that is CXL CXL system has, right? So in 1.1, right, we're looking at a single server, maybe a few CPUs, maybe a few CXL devices, all in what you would call a single node, right, or a coherent running a single OS, right? That's where we started from. From that, CXL 2.0 added some pooling capabilities. So we expanded to like maybe a rack level. So if you look at the picture on the right side, right? So in the beginning we were at just a server, then we got into rack, and with some of the technologies like Gen Z, they were trying to go far beyond that, right? They had a solution for a much larger fabric, and as Gen Z and CXL sort of are working together, some of the ideas, right, we incorporated in CXL, some of the use cases that Gen Z was able to address, also made its way into CXL. So we essentially now have a much larger fabric, right, that can span multiple racks and entire node potentially, right, to switch and even the two-level switch hierarchy, right? So this one shows the leaf switch and the spine switch hierarchy, and even maybe something about that, right? So again, in terms of the scaling as to how many nodes there can be in a single sort of CXL domain, it increases significantly when going from 1.1, 2.0 to 3.x. And within 3.x, right, there were improvements from 3.0 to 3.1 to 3.2, and we'll talk about that. So this sort of shows a simple picture of a CXL fabric, right? So again, it's a nice cartoon, but it shows multiple CXL switches that have connected to each other through sort of a non-tree type structure. Lots of connection going from one switch to another switch. Allows for things like failover and like traffic balancing. And then each switch can be connected to a node that can either be a CXL host, CPU, device, or even a PCI device, right? In many cases, as you know, that you can attach a PCI device in a CXL slot, right? And then essentially because it's the same right, same type of slot, right, for both of them. So 3.0 essentially enabled a non-tree architecture, as shown here. In 3.1, we went even further by enabling larger fabrics. That's kind of what I showed you, right? There's a new concept that was introduced called port-based routing that allowed the requester or the source to essentially populate the information for routing that allows for much larger fabrics. That came into 3.1. We also defined fabric attached devices, where you have fabric and you can essentially attach memory devices to it that are servicing requests from many hosts, right? In theory, up to like, I think 4,000 or something, really large number of hosts. We also beefed up our fabric management APIs because such a large fabric requires very careful management and orchestration. And without standard to manage such a large fabric, it can get out of hand, right? So the fabric management API section in the spec was beefed up quite a bit in 3.1. So these large size fabrics can be configured and operated efficiently. The other big advantage that CXL 3.x brought in was enabling peer-to-peer communication. Uh, so, as you know, there's just peer-to-peer communication is pretty common in the PCIe environment. So with CXL 3.0, we enable peer-to-peer comm between devices. So as shown in the picture here, you can have one of these devices. It could even be a PCI devices that's requesting access to memory on a CXL memory device, right, to switch without going to the host. So that was introduced in CXL 3.0. It uses the PCI unordered I/O protocol. Because it uses PCI unordered I/O protocol, the requester, like I mentioned, can be a PCI device as well, right? It doesn't have the CXL. Right? They work nicely together. And one of the key things that was added in 3.0 was ability for the target device to manage coherency. What can happen is that when a PCI device, a requester, asks for a cache line from the memory device directly going to the switch, it could happen that one of these hosts or CPUs may have cached it right in its local cache. So the device needs to get the latest copy from the host or CPU, and that was enabled by this what is called as back invalidation protocol extension that was added in 6.3.0. So that allows the device to get the latest copy and return the latest data to the requesting device, right? Therefore, make sure that it gets the latest copy, right? There's no cache coherency. So that was a major advantage, a benefit that 3.0 brought in. 3.1 went one step beyond and added peer-to-peer communication similarly to the switch, right? Using CXL.mem. Remember, 3.0 used PCI unordered I/O. 3.1 essentially added CXL.mem requesters, right, and responders, right, going to the switch without going to the CPU. So again, more efficient communication between CXL devices allows more efficient communication, more efficient performance, better, and lower latency in terms of accesses. The other really nice thing that CXL 3.x added was memory pooling. Technically, 2.0 defined some basic memory pooling constructs, but they had limited scalability. Right? So 3.x went way beyond and allowed a lot more flexibility and a lot more scalability in terms of memory pooling. So what memory pooling is, it allows a host or CPU to dynamically expand or shrink its capacity, right, to match workload. Right? Some of the workloads, they have uh, characteristics where this, right, for some amount of time, they need a lot more pages, a lot more memory, and once the burst, is sort of goes away, they don't need that much memory, right? So what happens without memory pooling is that all the nodes have to over-provision memory. They have to have the memory that's enough to handle the burst scenario. And during the other times, right, that memory is essentially wasted. Right? That is the what's called memory standard capacity problem, right? And that's really bad because memory is expensive, right? So wasting memory in a data center, in a I don't know 1,000 or 10,000 or even 100,000 right machines environment, right? These can add up. So memory pooling avoids that by allowing the memory from one device to be allocated to, as you can see the picture, right? The device D2 has some pages that are assigned to H1, host 1, some pages assigned to H2, host 2. And if host 1 demands more pages, it's possible to take pages away from H2 and then give it to H1, right? Pretty dynamically, pretty quickly. So 3.0 again defined a standard OS to device interface for requesting more pages, accepting more pages, and also file manager to device interfaces that allows the reassignment of pages from one host to another, right? Again, without these standard interfaces, right, it's very difficult to build a system that's successful. So the file manager that's shown here now can use standard APIs to talk to the device as a switch to make this happen very, very efficiently. And there's some examples out there, right, open source, right, that have been written to the standard. 3.1 went again one step beyond, and then also allowed fabric attached devices. Right, these are again like talked about large fabrics with lots of devices, thousands of devices, potential devices. They can be serving lots of hosts. so need a lot more scalability than the simple right, configurations. So some of these were added in Bharat 3.0. Again, really exciting feature. The other benefit that CXL 3.0 was memory sharing. Again, difference between memory sharing and pooling is that in the sharing case, a memory page is shared by multiple hosts right, at the same time. So as shown in the picture here, the device D1 has, let's say, two pages, S1 and S2. Both H1, host 1, and host 2, both are operating on S1. Host 2 and this other host is also operating on S2, right? So they both have a shared copy, allows them to do a much more efficient data exchange. And there's some primitives that work really, really well, right? Software primitives, right? Work really well with shared memory. So again, this relies on some of the back validation option we talked about that allows the device D1 to make sure each of the hosts has the latest copy of the memory, right? And none of the hosts actually gets confused or goes out of sync. So again, a really exciting feature. Again, requires a lot of software enabling. I know some of the software work is happening. There's some academia, right, work that's happening on enabling this. Again, this has a lot of promise and can change really, really how we write software in the distributed systems. So, an exciting feature. Again, we can't really talk about anything these days without its security. Right? So, heavy on security. So, here's the CXL answer. So, as I mentioned, right, as the workloads go to cloud, the owner of the workload or the customer wants to make sure that the data that is running in that virtual machine, right, that they hosted on the cloud, cannot be tampered with, cannot be leaked, right, by anyone, right, including the CSP infrastructure itself. So they want to make sure that there's a cryptographic separation between trusted VM and the CSP infrastructure. Infrastructure includes things like the hypervisor itself, management software that CSP may have, orchestration software that CSP may have, right? So they really want to make sure the data that's in the trusted VM is really protected, right, cryptographically. They also need for support for memory devices and accelerators, right? Devices for hosting memory that the VM has, and accelerators obviously for accelerating workloads, right? That the VM may be running, right? So we want to be able to use all of those, right, in the context of a trusted VM. Clearly, the data that's stored in the host doing use, meaning using computation, must remain encrypted. And there must be a way to verify that the system is set up correctly, right, to sort of meet these security promises. Right? So again, it has to be based on cryptography. So all of these things, right, were added to CXL in what we call CXL TSP, or Trusted Security Protocol. So it allows someone to build, again, the industry term for this is TEE, Trusted Execution Environments, that in a system that has CXL memory and CXL accelerators. So I show in the picture, so we have a TSP capable host that has some just regular VMs and a trusted VM. The memory, the color code shows the memory allocation, right? So the blue color shows the trusted VM and the memory that's assigned to that, and there's a separation between that and the rest of the VMs, right? Cryptographic separation. Again, this happens on the host side, but CXL extends that trusted VM domain to memory device as well. So if you look at a memory device here, it has again two sections. One section that's used by the regular VMs, and the one section of memory that's sort of cordoned off for the use of the trusted VM, and that provides all the security, right, guarantees, assurance that we just talked about. Between the two, the CXL link that transfers data supports encryption and integrity protection, as well as replay for called CXL IDE, or that was introduced in CXL 2.0. So IDE stands for integrity and data encryption. and just followed what was done on the PCI side. So this feature was in 2.0. What was added in 3.x was the whole TSP, or how to keep the data protected while it's in use. Clearly, we talked about it. It allows some folks to migrate the sensitive workloads to clouds without really worrying about the data being leaking. It allows, let's say, multiple parties, to collaborate on a single problem without really sharing the data, right? So if I have a data set A and you have data set B, I don't have to expose data set A to you, but someone can compute based on A and B together and come up with conclusions, right? So that's what this technology allows. There's also a number of compliance and sovereignty requirements that are coming up. These, again, maybe from the customers, maybe from some other nations, allows you to meet those. And it's just in general, right, allows better protection from the applications and as well as IP. So again, this was a lot of work went into this. This is a very difficult thing to accomplish, but I think a number of folks in the consortium worked really hard to sort of make it happen. So thank you for that. And again, just talk about how it progressed, right? So we built on top of IDE in 2.0, as I mentioned. 3.0 to the first step of adding TSP for simple memory devices. These devices rely on hosts for coherency management, but they don't really have their own coherency management. We had lots of these devices that are built in 2.0. A number of vendors have these devices. So it made sense to start with that as the first intercept. That's what we did in 3.0. Again, that was a big step forward. In 3.1, we built on top of that and extended that to cover accelerators, right? That use, again, they don't really use .cache. They're the ones that use .mem only, but can manage coherency. So now in 3.1, you have memory as well as accelerators, right? That can now be part of the trusted VM domain, and these workloads can benefit from that. 3.1 added some additional improvements to IDE. So there's some error information or poison message that we had that did not have ID protection. That was addressed in 3.1 to complete the picture. This allows IDE or security protections to work completely right, 100% right, in presence of some of these cases. And 3.12, obviously, importantly, right? So all of these things are really not being useful, right? Unless there's a conformant compliance test, right? That kind of ensures interrupt, right? The specs can be complex, right? So, and we'll get into compliance a little bit later, but it's really a key part of the CXL specification, which really have a good quality compliance test. So in 3.2, we introduced the compliance test for TSP. So this should help interrupt between hosts and devices and other components that are trying to intercept this feature TSP. Okay, so I think we talked about the features that sort of progressed from 3.0, 3.1 to 3.2. So let's talk about brand new features that made its way into 3.2. So one of the major enhancement that was intercepted 3.2 was CXL hot page monitoring, what we call CHMU. The primary use case was memory tiering. Before this, a number of companies had made some really good attempts at solving this problem, right? But all of them faced some common challenges. So before CHMU, when someone was trying to build a software tiering solution, they needed to trade off accuracy, which means how accurately they can track the hot pages, against performance overhead. If they wanted very high accuracy, they needed to spend more CPU cycles tracking hot pages, and they needed larger data structures in the main memory to track hot pages, right? So, which means bad for performance, right? And this was a really tough trade-off to make, right? And, but if they went for a really low performance overhead option, then they got terrible accuracy, and then the effectiveness of the the tiering solution kind of went down quite a bit. The other thing that was challenging is that since they were trying to measure the hot pages from the CPU standpoint, right, uh, the measurements were polluted by cache hits, right? It was difficult to sort of separate out accesses that were satisfied by the CPU cache versus the ones were not. And so the data was kind of somewhat, that could be somewhat polluted, right, and hard to make sense of. The third thing was these algorithms were CPU vendor specific. And again, that made it difficult to sort of scale in a large data center environment. So what the approach we took with CHMU was that, first of all, we started with the simple memory devices and pooling memory devices as the starting point, right? That's what we targeted for. The hard page trackers are implemented in the memory device itself, right? So as shown in the picture here, each memory device has what I call CHMU hot page trackers. So the device that's connected to the host has two such CHMU instances, right? And the ones here, this one has two, and it's a pooling device which has two, one for every host, and this device has a single tracker. So these trackers are essentially data structures that figure out which pages are more frequently accessed and keeps track of it. And I'll explain that in the next slide. So because these are the measurements happen in the CXL memory device, right? It avoids the pollution of the cache, right? I mean, you only track accesses that go to memory, and not the ones that are satisfied by the CPU cache. So that solves the other problem. Because they're in this memory device, again, there's no host performance overhead, right? The CPU is not doing any tracking, is not spending cycles trying to keep track of which page is hot. There's no overhead of the system memory to keep track of these things, so that avoids a performance issue. The interface is standard, so you can essentially build a generic OS-based solution for tiering that sort of works across multiple CPU vendors. And this allows the architecture allows multiple CHMU units, like I mentioned, as shown in the picture. So that gives software a little bit more flexibility. This is still sort of the emerging domain. A lot of exciting research is happening. So we wanted to provide enough flexibility for folks to do experiments and try out and optimize these algorithms. We allow counting at different granularity as well. Again, more flexibility is better. But in the end, right, so this allows someone to improve the software tiering solution. It's more efficient, and that essentially means better performance and lower TCO, because now you can use your lower cost, right, or maybe lower performant devices as a second tier and hide all of that overhead, latency overhead from the application. Digging a little bit deep into that, I mentioned about the CHMUs being highly configurable. So this allows software to make best use of these sort of critical resources. Right? There's not a lot of resources that the memory device can spend on tracking these. Right? So we have different ways to configure the memory device, so software can optimize what it wants to see, right, at a given time. So you can software can configure the specific DPA or device address granularities that tracking happens. It's called a unit. A unit size is configured with software, but it could be a megabyte, for example. A unit, the memory device will keep track of accesses and is marking it as hot if it exceeds the number of accesses that software is configured doing what we call epoch. So epoch length is set up by software. So software can, let's say, configure the device to say if we get more than 50 accesses during 100 milliseconds, right, or 1 second, that's how I define the hot page, right, and the device will follow that. And again, these things can be changed by software as part of the tuning, because different workloads, different environments may need different granularity, right, and different epoch lengths. So again, a lot of flexibility. You can essentially have tracking in multiple ranges that are not contiguous. So maybe software doesn't have resources to track hot pages for the entire device, for large device, but you can break it up into separate right, sort of ranges and then track them at that level, right? Again, a lot of flexibility. When the device decides a page is hot, it will add that to a circular structure called hot list. The counters are not given to software, but the hot pages are exposed to software. And software can either poll for the hot list right periodically, or it can ask the device to interrupt it when the hot list like starts to become full and it's going to overflow. So allow software to keep track of the hot pages efficiently, either polling or interrupted. And then software can also decide, hey, here are the types of requests that I want to count, right? I don't want to count, let's say we talked about TSP earlier. So there's certain types of CXL mem requests that are generated by a trusted VM. And maybe software doesn't want to track those, right? Because of the security concerns. So software can say, hey, don't track those. Only track the ones that came from the regular VMs, right? So that flexibility is provided to software. So again, a lot of work went into this. It took us about, I don't know, maybe 9 months to kind of work through all the details, the software model, right? And again, I can appreciate the effort by the consortium members in making this happen. We also added some enhancements going with PCIe. This is again a good example of how we work closely with other industry standards, right? So this ECN MMPT management message pass-through was really built by PCIe on top of some of the CXL 2 constructs, right? They made special accommodations for us for backwards compatibility, but again, excellent collaboration with PCIe. It allows standardized OS-based management of CXL as well as PCIe devices. So everybody wins, right? Because someone can build a standard management software that works for PCIe devices as well as CXL and don't have to reinvent the wheel for CXL. The other enhancement that was made, we talked about support for pooling in 3.x, and as the pooling devices sort of become more commonplace, it becomes important to make sure that a pooling device that's shared by, let's say, 8 hosts, an error in the pooling device does not bring down all the 8 hosts. Right? So this enhancement that we talked about here allows the device to specify which of the hosts is affected by the error. So the head ID and the LD ID field that are shown here, they can be used by the fabric manager to decide which of the hosts, right, is affected by the error and only, right, bring down that host or reboot that host, right, keeping all of the hosts, right, running. So allows a more localized error handling. So, and if there's a uncorrectable or fatal error in the memory pooling device, the blast radius of that is reduced, right, to maybe one host or maybe a couple of hosts, right, not all of them. So again, some of these things go hand in hand with enhancement that we talked about for memory pooling. But I think this intercepted to a little bit later than some of the other ones. There are other enhancements that we did for post-package repair, as well as improvement performance monitoring events that allows better performance analytics for memory devices, and also storage of the metadata bits. This allows us to optimize the number of metadata bits the device stores based on the host needs, right? So dynamically instead of wasting bits. So again, I will not get into that in detail now, but the slides are available and you can obviously look through that later. Again, looking at the summary, we talked about most of these. So 3.2 primarily added some of the security compliance requirements. So again, this slide I will skip in the interest of time. This is a critical one, right? So we did start official testing for 2.0 right, devices in December 2024, just a couple of months ago. So we do host test events, so the members can bring in their devices, right, to these events, and then prove interoperability, and then get listed on the CXL integrator list, right? So the current list is listed here, and I think last count we had like 48 devices on the list, right? The snapshot below shows kind of what's out there. but encourage you to go look at this link and then figure out which devices are listed. So again, this goes hand in hand. This shows the solid support ecosystem has of the CXL specifications and number of devices or vendors that are building devices to the spec. Right. Again, really great to see these some of the spec work that's been done turning into reality. Right, and folks are able to build devices that interact with each other. Again, quickly summarizing, we talked about 3.2 that added a number of security enhancements, compliance enhancements, and memory device enhancements. The memory device monitoring management optimizations, including the hot page monitoring, uh, other enhancements to the memory devices as well. A big thing was expanding TSP to address some of the input some of the ID protection, as well as support for accelerator devices, right? That use the HTM-DB or the device managed coherency protocol and compliance chapter additions for CSP, TSP interoperability. Again, this is where we are 3.2. We are, again, we're not stopping there, right? As we move further, right? We are actively working on the next generation of CXL spec. That, again, the key parameters we're looking at is increase the speed, again, to maybe again 2x of what we have right now. And there's other features that are improvements to AI workloads or memory expansion, as well as reliability and security. Those will be our key focus areas for the next generation, next phase release. Again, like I mentioned, 1.1, 2.2 devices are available today. You can scan the code to see right, where the device ecosystem is. But like I mentioned, there's a large number of vendors and devices that are out there that are defined in a compliance test. So I think with that, let's go to Q&A.
Excellent. Thank you. So now we'll go ahead and dive into the Q&A. If you have any questions, please feel free to submit them into the questions box. So our first question for today's Q&A is, how can I tell the difference between a CXL 3.2 device, a CXL 3.1 device, and a CXL 3.0 device?
That is actually a trick question, and I get that a lot, right? So if you look at the CXL specification, there is no registered bit or anything that says I'm a 3.2 device or 3.1 device or 3.0 device, right? And that's on purpose, right? There is no such thing as a 3.2 device, right? When folks say a 3.0 device, they generally mean a device that operates at PCI Gen 6 bandwidth at that speed, right? But other than that, pretty much all the other features that are seen by software, like CHMU, are discoverable independently. You could look at a device and say, hey, does this device support CHMU or not? And in theory, there's nothing that prevents uh, a, a PCI Gen 5 speed device, the one that's written to 6 2.0 spec, right, and that speed, from implementing the CHMU. Software doesn't really care, right? Software is going to look at CHMU capability and start using it, right? Whether the device is running at a Gen 5 speed or Gen 6 speed. So again, there is no such thing as there's no way to differentiate between them because right they are essentially one and the same thing. All the features that separate them can be enumerated separately, independently, and software can make use of them right, without really knowing which spec version the device vendor was reading when the device is constructed.
Excellent. So our next question is TSP compatible with other confidential computing technologies like TDISP?
So I think another good question, right? So TDISP is the PCI Express defined technology that allows, again, similar to TSP, trusted VMs to make use of the PCI devices, right, for computation and other work. Right? So TSP was sort of loosely defined on top of similar to TLS, uses a lot of similar concepts and similar constructs. Of course, the CXL protocol is quite different from PCIe, especially the dot cache and dot com aspects. So TSP had to do some additional work to kind of meet some of the security requirements that that need is met for PCIe. But yeah, they are conceptually very similar. There are other also technologies from different vendors, right? CPU vendors that for confidential computing. I think we have participation of multiple vendors in the consortium, so we believe those are also compatible.
Perfect. Our next question is, what are the benefits of OS-based software tiering over application-based tiering?
So when the system has different memory classes, right? Maybe one that's highly performant and one maybe not so. There are different ways to sort of optimize the usage of the page, right? So obviously you want to make sure your hot pages or frequently accessed pages are in the higher performance memory, and it can be done at either at OS level or at an application level. Right? Generally, the OS level approach is better because it's sort of done once and then benefits all the applications. You don't need to redo your application. You don't need to recompile applications. So have this work done in every single application. So that approach is generally better, scales better in terms of the enabling or ecosystem usage. So I think that's really why I think CHMU, our goal was to improve the OS-based tiering technologies. Of course, right? It's not CHMU is not limited, right? If your environment requires application-based hot page monitoring, it can definitely make use of CHMU. But we wanted to make sure that the standard interface that CHMU defines allows a pure OS-based memory tiering solution.
Perfect. For our next question, will enabling TSP have any performance impacts?
We had done our best to minimize the impact of the TSP on performance. So if you look at the IDE protocol, in order to encrypt the data, in order to send the integrity, and in order to process it, some additional work has to be done on both ends. It may have a small performance cost, but we've done our best to minimize the performance cost. In terms of the work that the memory device has to do for servicing the request, I think the tax is pretty small. It's generally accepted in the industry that adding the security is not free. There will be some trade-offs, some performance implications, and the industry tries as a whole to minimize the performance impact of the security technology, and that's exactly what we've done.
Perfect. Our next question, could you answer whether cache coherency is possible in TSP between the host memory and device memory using CXL?
The cache coherency is possible. So there's two ways to sort of manage the cache coherency. One was the traditional CXL.cache approach that was defined in 2.0 spec. The device has its own memory that is cache coherent with the host. Device can use .cache to manage the cache coherency, or in the 3.0 we introduced the back invalidation concept, right? That goes on .mem channel. So that can be used by device to manage coherency as well. The CXL spec allows devices that use the back invalidation based coherency to be supported. At this point, we don't have support for devices that use .cache, but yeah, you can use the .mem channel, the back invalidation feature to maintain coherency between the device and a host and still support TSP.
Excellent. Our next question, since a hot page is a function of the host/VM and memory pages, if it is on the memory that is shared, would it create a live lock situation?
Sorry, I'm not. Can you repeat the question?
Yeah, absolutely. The question, since a hot page is a function of the host/VM and memory pages, if it is on the memory that is shared, would it create a live lock situation?
Okay. I think maybe you're referring to the use of CHMU in case of hot pages, in case of shared pages, right? So shared memory is really, really special, right? You can't use shared memory as just like regular memory. So care must be taken when using shared memory. So, and I do not believe why you would want to use shared memory with tiered right, memory at the same time, right? It's just in a shared memory case, there's a memory device that has the shared page, has the memory location that is shared by multiple hosts, and they're both going to operate directly on that. Right? Don't expect it to be tiered at the same time. Again, if I didn't get the question, please feel free to email us later, and I'll try to answer the question.
Absolutely. I think we have time for one more question. So could you answer, how does the CHMU track coherency among hosts and devices?
So CHMU doesn't actually track coherency. CHMU is placed in this memory device and is monitoring CXL.mem accesses that the device sees. These are memory requests that device sees, and every time device sees a read and write request to a certain page or certain unit, it's going to increment the count. Right? So the coherency doesn't actually come into place here, because when the device sees the request, it's already has gone to the caches, has already coherency is already taken care of by the host.
Great. Well, that was the last question that we had time for today. So thank you again, Mahesh, for hosting the webinar. The webinar recording will be made available on the CXL Consortium YouTube channel, and the slides will be available to download on our website. Thank you again for everyone for attending, and have a great day.
Thank you, everyone.